All right. With limits, we can also do some things with absolute values. Of course, we know the basic absolute value. You've got the V-shaped graph, but if I want to show something about the limit of an absolute value, I kind of need to change it up a little bit. Let's just talk about the most basic absolute value here. Turns out with a limit, what I'm going to want to do with that is split that up and look at it from two sides, if you will, here. Two sides of the zero, where the graph V's right at 0, doesn't it, for that one? That's the V shape, and the V happens at 0. Well, the thing of it is, yeah, if I can describe that in more basic terms without the absolute values, that's going to be a good thing that we'll want to do, because actually what we're going to do is look at it from the left and the right, your limit as x approaches 0. But here's what we can do. I can actually rewrite an absolute value as a piecewise defined function. Two pieces. The first piece, let's go with the easier piece here. The first piece is the y function can be described just as x, because when x is greater than or equal to 0, doesn't your absolute value just equal the number itself? For example, if y equals the absolute value of 4, if x is 4, doesn't that equal 4? Y equals, if x is 5 or 15, that's what we're saying. The x is the answer for if x is positive or 0, same thing. That's what we're saying right here. Now, what happens if I turn it around and do less than 0? Well, if x is negative 5, say, the answer is still 5, but how does this compare to the x? Here x is negative 5. How does that compare to x? Well, it's the opposite, isn't it? It's the opposite of x. If x is negative 5, this is the opposite of that. Minus 5. Well, it works the same way for any negative number. You get a positive 10 there. So here's what I'm saying. If x is a negative number, then this is the opposite of that negative number. So if x is less than 0, it's minus x for the y value. With me on that. Okay? Now, what happens is if I shift it right or left and do some other things, but what changes is this the breakdown, where it breaks down the greater than and less than. Okay, but it works the same way. What if it was the absolute value of x minus 4? Well, what happens is that's going to shift it. You can graph it there on the TIs, whatever, but what happens is this gets shifted to the 4 there instead of 0, and so that means the break is going to happen at 4 instead of 0. Okay? Because another way you can look at it, this is really two lines, isn't it? This has a negative slope, this has a positive slope, and that's kind of verifies that. But yeah, so in this case, here's the negative slope, here's the positive slope. So yeah, the break happens at 4. Now, what happens then to this? Well, instead of x, I've got x minus 4, so that translates over here. If x is greater than or equal to 4, it's x minus 4. What about for x less than 4? Well, it's the opposite of the x minus 4, which of course is going to mean minus x plus 4. Okay? With me on that? Let's do one more. This one, plus, let's do the absolute value of 2x plus 5. There's a few other things here, but so I'm going to have 2x plus 5. I'm going to have a minus of 2x plus 5. Where does the breakup occur there? 5? Well, notice it's going to be shifted to the left with a plus 5. That's one thing, and then actually this too has effect on it. But that's what I would tell you is look at your graph and see. So absolute value, that's on the TIs, it's under math. Num. Absolute value, all right, 2x plus 5. Or get some points, whatever. Yeah, so it's over here. -1, -2, yeah, it's halfway. It's actually at -2.5 there. So anyway, you can use your calculators as you want, but so the break here is going to be at -2.5. Okay. And there are some other things we'll probably revisit later on. Oh, I went off the screen here. Oops. That's about as far as it goes. All right, let me rewrite this. Let's see. Can I squeeze that in there? I don't think so. All right, so this is y equals x minus 4. That's x minus 4, x greater than or equal to 4, negative of x minus 4, x less than 4. And then this one, y equals 2x plus 5. It's 2x plus 5. You got x is greater than or equal to -2.5, and then negative of 2x plus 5. If x is less than -2.5. See if I got that on there. Pretty well. Okay. All right. But anyway. Okay. So let's see why we want to do that. If I want to talk about then a limit of an absolute value, let's do this one. Limit x approaches 1 from the right of the absolute value of x minus 1 divided by x minus 1. Right there. Okay. We can look at, matter of fact, we might have, well, we looked at an absolute value once before using a table. But without using a table, what we can do is utilize what we've been talking about here. Depending upon, of course, the break happens. Of course, the bottom goes to 0, as normally happens. So I need to get rid of that little thing to verify this. But here's the thing. To remove those absolute values, that's what I want to do here. Remove the absolute values by using the piecewise defined function for the absolute value of x minus 1. Because on either side, the absolute value of x minus 1 is either x minus 1 or it's minus x minus 1. Removing the absolute value bars, that's my two options. Now, I use this option if what? If x is greater than or equal to 1, right? And I use this option if x is less than 1. Which option do I use here? Well, I'm going 1, approaching 1 from the right. So is that 1 from the right? Is that the greater than side of 1 or the less than side of 1? That would be the greater than side of 1. Approaching 1 from the right would be the greater than side of 1. So that tells me that in this case, use the x minus 1, which is nice. Okay, it's just x minus 1. In other words, I can just remove the absolute value there. Now, why does that help me? Well, now, whereas I couldn't before because I couldn't cancel those out because of the absolute value, if it was the absolute value over the absolute value, I could cancel those out, but that would be not a very interesting problem, but I could. But since that one's an absolute value and that one's not, I can't just cancel those. And we'll see why here in just a second. But since it is going from the greater than side of 1, I can just say that's x minus 1, which means I can cancel those out. And so this is the limit as x approaches 1 from the right of just 1, which is 1. Okay? All right. 1 from the right. And that's the greater than side of 1. So I'm going to use this. Now, if it had been 1 from the left, well, I would use the other one. Okay. All right. Well, let's do another one. All right, let's do the limit as, let me do it over here because I won't have enough room over there. Is that okay? Is everybody got all that they want? All right, the limit, x approaches -3 from the left of x squared minus 9 over the absolute value of x plus 3. Which, of course, again, the bottom goes to 0 if I substitute in, so I've got to do a little bit of work. Okay, well, there's two things of note here. On the top, what do you think? I'm going to need a little factoring. Back to the top, difference of squares, x minus 3, x plus 3. And on the bottom, I've got absolute value, so I'm going to use that absolute value piecewise defined function. And so I've got either x plus 3 or minus the x plus 3, which, you know, it's just the basic one. This is if x is -3, greater than or equal to -3, and this is if it's less than -3. Which one is it in this case? It's the negative, isn't it? I'm approaching -3 from the left, and so that's coming in from the less than side of -3. That's going to be, to take the absolute values out in that case, I need to take out the, replace it by a negative of the x plus 3. You can see why I write that. Instead of distributing the minus, you see why I leave that without the minus distributed, because now what happens? The x plus 3's cancel out, yeah. And so I'll wind up with the limit x approaches -3 from the left of x minus 3 over -1, hey, yeah, now I can just substitute. It's negative 3 minus 3 over negative 1, which gives me negative 6 over negative 1, which is 6. Okay? All right. Well, let me piggyback off of this little work here, and let's ask a second question on this. Does the limit as x approaches negative 3, x squared minus 9 over absolute value of x plus 3 exist? And if so, what is it? Or if not, explain why. Well, does this mean the limit as x approaches negative 3 is 6? No, it just means as x approaches negative 3 from the left, it's 6. What else do I have to check for this one? I got to check it from the right. So let's see, the limit as x approaches negative 3 from the right. I've got to check that because on the piecewise, remember we've got to look from the left and the right. So it's about the same, isn't it? X approaches negative 3 from the right would be, well, I'd factor the top. But then what about the bottom? Well, since I'm approaching negative 3 from the right, back on that piecewise, which one am I going to use? I will use the top, won't I? Because I'm approaching negative 3 from the right, so that's the greater than side of negative 3. So that is the x plus 3 side. So it's just, there's no negative on that one. That's the difference, and of course that's going to make a difference in my answer, right? Because now it's just going to be the limit as x approaches negative 3 from the right of x minus 3. So yes, that's just going to be negative 3 minus 3 is negative 6 for the limit from the right. What does that tell me? That's going to tell me the limit from the left is 6. The limit from the right is negative 6. No match. So, does the limit exist? Is x approach? No. Remember, we did one like this before. We used a table. Remember, it came in from the left. Well, in this case, it came in at 6, and then it came at negative 6, positive 6 on this side, negative 6 on this side. So it did come in, meet up. You know, if it has a limit, the limits meet up from left and right. But this one, it came in one from the left, one from the right at a different level. So, but this gives us a way to prove it, if you will, or to write it more algebraically. Okay. Okay. For some reason, I think I should mention this. If I have, just so happen to have, you got to be careful on those piecewise. If I have, I think I should have left that one. But if I'm talking the absolute value let's think about this. The absolute value of 3 minus x. I think you have to be careful with your x greater than or less than. Let's see. The break's going to happen at 3, but let's think about it. 3 minus x. Absolute value of 3 minus x. I think that looks like this. Let's look at it. on the calculator here. Absolute value of 3 minus x. The absolute value of 3 minus x does come in looking like this. Yeah, this was a little tricky because notice this one has the negative slope, doesn't it? Isn't this negative slope line? Which one of these has negative slope? The top one, because it's a minus x. Which side is that? That's less than 3, isn't it? So yeah, that's what I was saying. If it's something kind of funny in there, be sure you check it. And that's one way you can look at it. This one has a minus slope. This one has a positive slope. So this one is the one that's greater than, because it has a positive slope. Minus makes it plus. This one has a minus slope. So, but yeah, there's some different weird things that can happen. So just be sure to get your. I don't know that comes up, but just in case I want to mention. All right. The other thing I wanted to mention was here the greatest integer function. Perhaps you've heard of it, perhaps not. But now you will have. The greatest integer function. It's denoted with, I think our book does the double bar bracket thing. Sometimes you do just see it, sometimes you might just see it double bars, sometimes you might just see it bracketed. But anyway, this is what it means. This is the way the book denotes it here. But anyway, it means if you have the greatest integer of x, that means you want the largest integer that is less than or equal to x. So basically it's, what integer is this one close to without going over, I guess you might say. The largest integer that is less than or equal to x. So here's just a few examples. I have the greatest integer of, and of course if it's just a number, an integer itself, it's the greatest integer of 2 is 2. But if I go the greatest integer of 2.1, that's also 2, right? Because the integer that's less than or equal to that, the largest one, would be 2. And so that would go up until, even at 2.9, the greatest integer is still 2, because I can't go greater than it. It has to be less, the integer I get here has to be less than or equal to it. So I don't change to 3 until I get to 3. The greatest integer of 3 is 3. And then 3.1, 3. So forth and so on. Okay? So that's the greatest integer. Now, careful on the negative side here. The greatest integer of negative 5 is negative 5, just like you'd hope. But what's the greatest integer of negative 5.1? Is it negative 4? Is it negative 5? It's negative 6, yes. That would be negative 6, wouldn't it? Why? Because negative 5 is actually greater than negative 5.1. Right? Think of the number line here. Here's negative 5, negative 6, so negative 5.1 is here. So yeah, negative 5 is actually greater than negative 5.1. So the greatest integer is not negative 6. Negative 5, it has to go back to negative 6. Yeah. Okay, so be careful on the negative side of things. It's the same, but it's sort of different. Okay. All right. Reason I mention it here is because this one has a nice little graph. Let's talk about the graph. Y equals greatest integer of x. Okay, well, we kind of started, I guess, because yeah, if you look at a table, we were doing 2, so this would be well, let's just start at 0. Forget that. When x is 0, the greatest integer of 0 is 0. We got 0.5. Greatest integer is 0.5. What would that be? 0. 0.9. So until you get to, that's also 0. Until you get to 1, the y values are all 0. At 0, you're at 0. Here's 1. 0.5, you're at 0. 0.9, you're at 0. So all the way up until you get to 1, you're at 0. And then at 1, it jumps up to 1. So there's an open here and a closed one there. Then what happens from 1 to 2? Well, from 1 to 2, you go across to 2. At 1.5, it's 1. 1.9, it's 1. 1.1, it's 1. So it's 1 all the way across till you get to 2, and then at 2, it jumps. Till you get to 3. And then at 3, it jumps to 3. And then at 4, it jumps to 4. With me on that? So you get these nice little stair steps, sometimes referred to, I guess, as the stair step function. One of them. There's others, but this is one of them. Now, what happens back here? Well, that's what we were talking about. If I go to negative side, negative 0.1, well, at negative 0.1, that's what we were talking about. That's not 0, because 0 is actually larger than negative 0.1. So what's the greatest integer of negative 0.1? Well, that's where you have to, on the negative side, you kind of have to go backwards thinking there a little bit, but it's negative 1. Yeah, so this, from 0 to negative 1 on the x, this levels out here. And then notice at 0 it's open, and negative 1 it's negative 1. So yeah, it's the same. You got closed on the left, open on the right. Circles. And then from negative 1 to negative 2, it jumps down to negative 2. Right after that. So it continues the stair step. Okay? And there is, on the TIs, there is a greatest integer function. I think it's under math as well. And let me talk about that. Math and num. Yeah. If you go to math and then num on the TI, it's number 5, I think. INT. It's the greatest integer. And if you do that here, on most of them anyway, forgot to do it. Quit that. Math, num, number 5. X. So the INT of x is the way it looks on here. Notice it's a little misleading because if it's in connected mode, which most of them are, it's going to connect. It's going to go here. It's going to start down here, and then it's going to connect kind of up here, and then connect up here. So it actually does make stair steps, but just be aware that those really, it's just connecting this point to that point, which it shouldn't, but it does. Okay, it doesn't know not to, unless you tell it to. But you get that. Of course, you don't get the nice little open and closed circles like I would expect you to put in there. So it does a pretty good job. Okay, so why do I mention that here now? Well, since we're talking about limits, what about the limit as x approaches 5 of the greatest integer of x? What would you say there? Well, hopefully you kind of see here that you got to look at the pieces, don't you? Because does this limit exist? No, it doesn't. This limit does not exist. As you approach 5, which I didn't quite go out here to it, but what's it doing? As you go to 5 from the left, you're coming in here. As you come to 5 on the right, you're coming in here. So what's happening? The limits aren't agreeing. Yeah, you got the limit as x approaches 5. Here's what you could say then. The limit as x approaches 5 from the left of the greatest integer of x, what is it? As you approach 5 from the left, then you're coming up here, which is 4, right? The limit as x approaches 5 from the right, as you approach 5 from the right, well, you're coming in at this level, which is 5. So the limit from the right is 5. The values here are coming in at 4. The values here are coming in at 5. So the limit as x approaches 5 does not exist of the greatest integer of x. Whoops. With me on that? Okay. Now, yeah, okay. And then, there's really not, we did it kind of with a table here. If you wanted to show some work on this, you could use a table. You could use the, I don't know if it'll ask you to prove it or whatever, but not just a real nice way of doing it, other than by examining a table. But I mean, you get the idea. But yeah, if you come in here, the x value is less than 5. So if you go 4.9, 4.99, 4.99, as you approach 5, all these values are 4, right, for the greatest integer. So that's what I would say if it asks you to use a table or something like that. Just go back to approaching 5 from the left, and then you do the same thing, 5 from the right. Okay.